So when we talk about membrane structure, that's where we're talking about the fluid mosaic model. So our phospholipid bilayer with hydrophilic and hydrophobic parts, phospholipids made of glycerol heads and fatty acid tails. This is where we talk about carbohydrates and cholesterol, integral membrane proteins, and the functions of all of those things. You are not expected to draw a membrane. But you should know the parts and what they look like. I don't know how to make it more obvious. Was that obvious enough? Okay. When we finished with membrane structure, we talked about how membrane structure makes one of the most important features of a membrane, selective permeability. So when we talked about selective permeability, we talked about the different methods or ways things can go through a membrane. The different ways they can go through a membrane are through passive transport or active transport, where passive transport was broken apart into diffusion, facilitated diffusion, and osmosis. It was broken apart into diffusion, facilitated diffusion, and osmosis. And we said things about passive transport like it doesn't require energy and it moves down the concentration gradient. And that it's going to stop once we reach equilibrium. We compared that to active transport where we said, well, active transport, opposite land, moves up the concentration gradient, requires energy in the form of ATP, and is for large things, like really big things or charged things. That's how we get them across the membrane. Our passive transport slide, it's a summary of things that we're familiar with. The idea of moving down the concentration gradient, like going down a hill, riding your bicycle down a hill, takes no effort. Everybody likes the downhill on a bicycle. You get to coast. So there's no energy required there, and it's until equilibrium is reached. Here is when we had a lab. So these scenarios are like your lab scenario. You are looking at the cells that you made in your lab and the beakers that you placed them in. And we're going to use some words that you should have defined as bell work on Thursday and today. Here we are looking at the concentration of salt inside a cell and outside of a cell. And the salt, it occurs in a solution, which means it's been dissolved. Salt can't move across the cell membrane because it's charged. When it's dissolved, it has a charge. So instead, we have to look at the thing in the solution that can move across the membrane. Water can freely move across the membrane. If inside the cell is 5% salt, how much water is it? 95 has to add up to 100%, so it's 95% water. If outside of the cell is 5% salt, what's the concentration of water? Is there a concentration gradient? There's no difference, right? Same on the inside, same on the outside. So there's no net movement. Nothing has to move in, nothing has to move out, because it's the same. It's already at equilibrium. So we can label this with a vocabulary word. First we say there was no net movement. And then we can refer to it by a special vocabulary word that means same concentration. If the solute, so the thing that is dissolved, if it's the same inside and outside, we call it isotonic. Iso, like an isosceles triangle. Iso means equal. And the cell stays the same size because there's no net movement, there's no change in pressure inside or outside, all the same. Was that the case in your lab, that there was no net movement?
Would that be
Mm-hmm.
passive?
So these are all passive. Here we have a different scenario. It's 10% salt and 5% salt. But remember, salt can't move. What can move?
Water.
Water. So what's the concentrations of water here?
90.
This is all passive transport, which means it's moving down the concentration gradient, or from high concentration to low. This is going to be the hardest math you've done all day. Which one is higher, 95 or 90? Sounds like a trick question, right? 95 is higher. So we move from where it is high to where it's lower. So does water move in or does water move out? Water is going to move in. And since this is a cell, there's two choices. If it's a plant, it's going to swell and increase in turgor pressure. So it swells and increases in turgor pressure. If it's an animal, there's no cell wall forcing it to not explode. So it explodes, bursts. This process of water moving in and out is affecting the amount of cytoplasm, right? So cytoplasm is what there's going to be more or less of in volume based on what moves in and out. So we call this plasmolysis. Plasmolysis, plasm, right? Cytoplasm. Lysis, to cut. So, you know.
What's plasmolysis?
This process, when things move in and out, changing of pressure, because it affects the volume of cytoplasm.
What's turgor pressure?
It's the increase. So, you know how if you took a water balloon and you only filled it with a little bit of water, it's not very firm? But if you put more water in it, it's very firm. You've increased the pressure inside of the balloon, right? So turgor pressure is just the amount of pressure exerted upon the cell wall based on the amount of cytoplasm.
It's an example of an animal cell bursting is when it's not when an animal cell is at the bottom of an ocean and the pressure is too much.
No, what this is something more like if you were to have gone to the hospital for dehydration. They don't give you an IV of water. Most people are like, well, yeah, I'm dehydrated. Water is the obvious thing I need. Water is actually the last thing you need because inside of your cells will be higher in salt concentration than the outside would be if they put pure water in you. And pure water would cause your cells to explode, which is why if you ever get an IV because you're that dehydrated, it's not pure water. It's labeled saline solution because if they put pure water in it, they'll just make your red blood cells explode. So you went to the hospital because you're dehydrated and you leave the hospital because you're dead. You know, details. Seems bad, right? You agree? Not good? It would be exceptionally difficult and very rare. Most often plant cells will burst because they've frozen. The water inside of it is frozen and punctured holes in their cell wall.
Can your stomach burst as well? If you drink too much water?
Yeah, you can die of water poisoning, absolutely.
What is it? When your stomach's too much water in it?
Well, you could drink too much water.
Yes,
Yeah.
you can die of water poisoning. It's possible. This will kill you if you drink too much water. But we're talking like gallons and gallons and gallons of water. It's not impossible, but it's improbable.
So with the first case, where
This is passive. Well, it doesn't require energy. It just naturally happens.
oh, okay.
Sorry. We called the last one isotonic because iso means the same. Here, the concentration outside was lower, so we call it hypotonic. And that just means less concentrated. Remember though, it's not the concentration of water that we label isotonic, hypertonic, hypotonic. It's the concentration of whatever is dissolved in the water. We determine net movement based on the water, but the hypertonic, hypotonic, isotonic is based on solute. Last potential scenario here, we've seen, you've seen one where there's no net movement. You've seen one where movement goes in. There's only one other choice. What's your hypothesis for this cell?
Moving goes out.
There's his hypothesis. Shall we check it? If it is accurate, what is the concentration of water inside the cell versus outside? Is it going to be higher inside or lower?
Higher.
95% water inside, right? It has to add up to 100. 90% water outside. Water rushes out, the cell shrinks. This, my friends, is why I would never allow you to do an experimental design where you asked me how salt water affects the growth of a plant. I already know what's going to happen. You make water rush out of the cell, the plant is going to wilt, the plant is going to die. It's a matter of understanding cell tonicity. This instance, higher solute concentration, hypertonic, higher hyper. So hypertonic is for higher solute concentration. All passive transport, all just happens until we reach equilibrium. If it's attempting to reach equilibrium, it's passive transport. Active transport doesn't attempt to reach equilibrium. Active transport, we said, opposite of passive. This is riding your bike uphill. Riding your bike uphill is lame. No one likes it. No one likes going uphill. Why? It takes work, right? Work is just the non-science term for energy. It takes energy. And it's going to be moving large and charged things. Moves large and charged. Active transport with which you should be familiar, our sodium-potassium pump, which we watched together, but we'll take a look at again today, as well as endocytosis and exocytosis. The suffix cytosis, C-Y-T-O-S-I-S, means cell. So endocytosis means enter cell. Exocytosis means exit cell. The two types of endocytosis just refer to the kind of thing being taken in, whether it's a solid or a liquid. If it's a liquid, we call it pinocytosis. If it's a solid, we call it phagocytosis. It's the only difference is the state of matter that's being taken in. The method is still the same. These are more easily seen in illustration than they are spoken about, so that's why we have the videos.